Thank you. Thanks, everyone, for coming. And also, thanks for organizing this great meeting. It's great to see everyone. This is going to be the second handwritten talk of the conference. And after Alejandro, your eyes are, I'm sure, super sharp. So enjoy. So let me start by giving an outline. So I'm going to be talking about, first, I'll just introduce Hamilton-Jacobi equations and their defined homogenization. But I'll use the term a little loosely. I will talk about inviscid and viscous equations, means first order and second order equations. Normally, Hamilton-Jacobi equations are first order, but I'll take the liberty like this. And then I will talk about classical results of homogenization in this context. So when the medium is periodic or when the Hamiltonian is convex. And then I will switch to non-convex Hamiltonians, where things are more difficult, and where I will briefly mention some positive and negative results in dimensions 2 and higher. So homogenization can fail. And then second half of the talk actually will be devoted to which one is the laser pointer here? I don't know. This one, yeah? OK. So d equals 1 will be the second half of the talk, where there are general homogenization results. And so the result in the second order case, the viscous case, is new, and it's joint work with Elena Kosygina. And I will also mention the qualitative differences between inviscid and viscous homogenization in dimension 1. So the kind of equation that we'll be considering is a case like this. So H is the Hamiltonian. It takes the gradient of the solution. So we are in d dimensions. And here they have an A. It says symmetric non-negative definite matrix. So take it a multiple of the identity. It can be 0. In that case, this drops. So you have a first order equation. And I'm not going to tell you all the conditions we're going to impose, but just keep in mind that the Hamiltonian, you want something that, say, grows superlinearly in P. So that is some kind of coercivity. And keep in mind, this example is a rich class of examples of what we call separated Hamiltonians, where we have a function g here, and this v, think of it as some kind of potential. And of course, this is the classical case, where we have a quadratic, which is, of course, superlinear. Now, the name Hamilton-Jacobi comes from these original works of Hamilton and Jacobi in the context of optics and mechanics, where the first instances of such equations appeared, but it was all first order. Now, speaking of first order, if you actually want to see where these things appear, so optimal control is a very important subject, where you basically have some expression and you're minimizing over some class of control policies, so inf dot dot. I'm not going to really introduce a notation. When you do that, dynamic programming gives you a Bellman equation. It's called the Hamilton-Jacobi equation, where H is convex. Now, if you introduce a second player and they do inf sup, so this is a zero-sum differential game, then actually you get what we call an Isaac's equation. It's a form of a Hamilton-Jacobi equation where H is no longer necessarily convex. And in fact, you see these are double-sided arrows because for every convex H, you can write an optimal control problem. For every general H, you can write a two-person differential game. Now, this is in the inviscid case. So, so first order. So this notation, this terminology comes from fluid mechanics, where if you want to now look at the viscous case where you have a second order term, then that kind of equation shows up if you're studying stochastic optimal control, meaning that now you have an expression, but the expression, there is a controlled Markov process, and you're taking an infimum of the expectation of this, where again, H would be convex. Now, the most general thing would be a two-person zero-sum stochastic differential game where you have a second-order term, A is positive, and H is general. Yeah. So meaning for every H that you give me with some minor conditions, I can write a two-person differential game where that game is governed by some Hamilton-Jacobi equation with that H as the Hamiltonian. There's a general theorem like that. No convexity. Yeah. Yeah, exactly. If you want convexity, you can actually, it's enough to have only one player. Yeah. Now, so we're going to suppose that A and H as a function of X, right? So these are random, so it's a random medium. Okay, and so we have some underlying probability space where omega is kind of representing that. And so, and this is a stationary ergodic field, or environment, medium. We just use these interchangeably. And we will scale space in this fashion. So we will have, wherever you had x before, you will put x over epsilon. So when we scale, and we also, I will explain a little bit why I also want to put an epsilon in front of the second order term here. Okay, and we want to send epsilon to 0 and ask what happens. Okay, and what we expect is that because we are in this stationary ergodic setting, and when we scale, there should be some kind of averaging, but a very nonlinear averaging kind of kicking in, and then it should, all these crazy oscillations should somehow cancel out in some way, and then we want to get a simple equation. So this is the question of homogenization. As epsilon goes to 0, does this equation effectively become an equation like this, where thanks to this epsilon in front, this just goes away, and thanks to these crazy oscillations where the frequency is kind of, faster and faster, where they kind of drop out, and now you have some new function h bar. Okay, so of course, so this function h bar, we call it the effective Hamiltonian if this thing happens, and it no longer has any randomness in it because of ergodicity. That's the expectation. So if this happens, we say we have homogenization. Now, why do we have this epsilon in front? Now, it's a totally respectable thing to consider a question like this as well. But this one is very much related to various models like random walk and random environment, graded polymers, their large-scale behavior, large deviations, free energy, the kind of stuff that Alejandro talked about. So I will mention that connection a little bit as well. So now, what does it mean for this equation to actually effectively become this equation? What does that mean? It means that the solutions of this converge to the solutions of that in the following sense, very briefly. So for so you decide to work with a certain set of initial conditions, let's say uniformly continuous, and then you take the unique viscosity solution of the scaled Hamilton-Jacobi equation and the unique viscosity solution of your target effective equation. And so the notion of viscosity solution is kind of inspired or motivated and tailored to Hamilton-Jacobi equations, a beautiful notion that bypasses differentiability. And so with the same initial condition, you want to basically say that for all such initial conditions, you have that this solution converges to the target solution locally uniformly. So that's what we want to prove. So as I said, there are classical results. So first, the setting is we will assume that the medium is periodic. So one periodic, for example, in each coordinate, that means we're living in a torus. So in this case, the pioneering work of Lyons, Papanicolaou, and Varadhan considered the inviscid problem and proved homogenization. And then it was adapted to the viscous setting by Craig Evans. Now, just want to briefly mention how this goes, because it's important for the rest of the talk. So what's done is, so this is a static version of the Hamilton-Jacobi equation where there is no longer a time derivative. You see, it's replaced by a constant. And so the rest is the same, except I also squeezed in a vector theta here. So, and here's an assertion. For every theta, there is a constant lambda that depends on that theta, and a periodic solution to the static Hamilton-Jacobi equation. So this is an assertion, and you first prove this assertion. And it's proved using the compactness of the torus. Okay, and that there is a lambda, okay, like that for every theta. Now, once you have that, you're in good shape, because then you can define a function of time and space, which is linear here, of time and space. And this solution that, in this assertion, this solution is called the corrector. It's called the corrector because you take this linear thing, and then you correct it in this fashion. After that, you check that this function of time and space solves the scaled original Hamilton-Jacobi equation. That's no surprise because this solves the static version, so it's like a reverse engineering thing, if you like. And then this linear part very trivially solves this Hamilton-Jacobi equation. But so then if you remember the definition of homogenization, in the definition, we really had, right, this H bar is the effective Hamiltonian, so appearing in that equation. So now you see this lambda that from that assertion I told you, that lambda now looks like that's our effective Hamiltonian. Okay? But remember that in the definition of homogenization, you have to have the same initial condition, right? But these guys don't have the same initial condition, right? So this one has theta.x linear, but this was linear plus this corrector term. But when see, this is a periodic function on a torus, so it's bounded, continuous, so bounded. So with the epsilon, so it goes to 0, right? So this term goes to 0. So by a comparison argument, actually, you can make things work, and we do have homogenization, at least with linear initial data, which then with a separate argument you can generalize to uniformly continuous initial data. So moral of the story is that if for every theta there is a lambda, right, if that assertion and then a corrector, then homogenization works. Okay. But for every theta there is a lambda, okay, but that's not explicit. Okay, so that's like, we need to keep that in mind, that it's not really telling us what this effective Hamiltonian is. Okay, so now if we step away from periodic media, we were non-periodic random media, then, actually we can realize that, for this argument to work, I didn't need F to be bounded. If actually F is if F grows at most sublinearly, then this would also go to 0 as epsilon goes to 0. So then we can kind of relax this thing. I think this was an observation in one of Freydon's papers I read. So, right, so this is kind of a hope, right, that you would want to kind of get away with that. But that, you cannot find, like for every theta, a lambda and a sublinear corrector. You just, there are counterexamples. So unfortunately, this strategy fails like off the shelf. Okay? So then, nevertheless, you can make like an orthogonal assumption, right? This time about the dependence of the Hamiltonian on the gradient variable. So we use P because classically P is reserved for momentum, so the momentum variable. So if H is a convex function of P, remember it was periodicity is about X, right? Now this is about P, the other variable. Then actually we have homogenization. And so this is another kind of classical area. So there now remember, what does convexity buy us, right? So convexity means I can write a control representation for the solution. So that is what's used here. There's an optimal control representation, which then, once you have that formula, you can analyze using either the subadditive ergodic theorem, as is done in these 3 papers. And in this paper, Srinivasa Varadhan used large deviation techniques to prove homogenization. And so actually, all these works show that H bar, the effective Hamiltonian, is convex. And so remember, this was convex by assumption. The original Hamiltonian is convex. The effective Hamiltonian is convex. And you also get a variational formula for the effective Hamiltonian. Now, actually, this paper here, because it's using light deviation techniques, there is an upper bound, lower bound, and matching them. So actually, you get two variational formulas. And this paper has inspired a lot of work in large deviations of random walks in environments, quench-free energy of directed polymers, and also there was a sequel of this paper by Kosigina and Varadhan for time-dependent. That was used for the directed models of statistical mechanics. And both of the variational formulas that you get from lower bound and upper bound have been also analyzed with all these Boozman functions and all that. You know, we had a series of papers with Firas and Timo and other people have worked on it. So it's been a very fruitful research area stemming from this paper. Now, but I want to focus on now non-convex Hamiltonians. So, of course, in this case, right, you do have a differential game in super representation for the solution, but so far, I don't think it has been put to any good use to be able to prove, you know, as far as I know. Now, and in dimension greater equal to 2, there are some positive results, meaning that homogenization has been established for in certain cases where the Hamiltonian is not convex, but it has certain structural properties, maybe radial symmetry, where it has bumps, but the bumps have a certain profile, and it has to be in such a way, and in that case it works, but if you change it a little bit, you know, the proof doesn't go through. Like, these are not very robust results. For a very good reason, because there are also counterexamples to homogenization. So there are actually Hamiltonians that are totally fine, coercive, non-convex coercive. So the first one is due to Ziliotto, who's a game theorist. I think is your colleague, right, Stefano? So, and he came up with this two-person game where H ends up having a saddle point, and there's a slowly mixing environment, and then you just don't have homogenization. So it's a very sobering result. So whatever we have to do, we have to be careful. Now, so in dimension 1, you can have a saddle point. That's great. So, and in fact, in the inviscid case, in the first order case, a general homogenization result has been published now already 8 years ago. And the viscous version of it was open until recently, and that's our new result, which I'm going to present. Now, in general, like the viscous one, the second order one, is always more complicated, right? Because you just, you know, and so far, whatever kind of holds true in the inviscid case, you know, after certain years of more effort, kind of you prove it in the viscous case. So that has been the pattern. You know, it requires more work, but qualitatively has been the same. But I'm going to also show you that now we have this phenomenon that shows that there's a qualitative difference between first order, second order. So please keep that in mind as I continue. Okay, so what I want to do is I want to actually now focus on one dimension. So I'm going to drop the matrix notation, so you just use lowercase a from now on. And I want to first present these two results kind of together. Okay, what's the statement? And then I'm going to kind of separate them after that. So this is the static Hamilton-Jacobi. So this is the static Hamilton-Jacobi equation. Remember that this was instrumental in the work of Lyons, Papanicolaou, and Varadhan. But now, what I want to do is I want to take advantage of the fact that we are in 1D. So I want to give a name to this here. I want to call it lowercase f, because then I can recognize that, oh, and then this is just a derivative of that. So now I have a first order ODE, because x, right, is just space. There's no time. So x is 1D. So I have a first order ODE, right? It's in 1D. Okay. So I will call this the auxiliary equation. Now, of course, A can be 0, in that case, it's not even ODE. Okay, it's just like some kind of inversion you have to do. Okay? Now, I want to, again, be inspired by Lyons, Papanicolaou, and Varadhan. I want to say, okay, they said that for every theta, there's a lambda, blah, blah. I want to give a name to the set of all good theta. Let E be the set of all good theta. But now, I want to actually be even more demanding. I want to, what was a good theta? Means there's a lambda, and then there's a sublinear corrector. Now, I want the sublinear corrector to have a stationary derivative. An extra condition that I want, okay? So you see that's exactly here. I want the derivative, right? The derivative to be stationary. And now I say I want the expectation of this to be theta. Of course, by ergodic theorem, they'll be growing like theta to x. And this theta is already separated here. That means this capital F will be sublinear. So this is the same thing I'm saying. Okay, just take my word for it. All I'm saying is this is exactly the kind of stuff that Lyons, Papanicolaou, and Varadhan had. But now I'm throwing the extra property that I want the gradient to be also stationary. And well, in their case, the correctors were periodic, hence stationary after you, of course, randomize the starting point. So in their case, in the periodic case, E, right, the set of all good theta is all of R. Right? So everybody is good. Okay. Now, in our case, not everybody is good. It's like a good movie. You can't have everybody good. So in our case, what happens is E actually, in our case, I mean like in both cases. Okay, inviscid and viscous in both cases. So E actually possibly excludes some intervals. Okay, and then the effective Hamiltonian has a graph like this where, so H bar, the effective Hamiltonian, is constant on those intervals that are not part of E. So whenever you have an interval that's not part of E, the effective Hamiltonian is just constant on such intervals. Okay, so that's the common picture. That's both for first order and second order in dimension 1. Okay, but now I want to get into the story in a little bit more detail. Now I want to focus on first order. Okay, this is the work of Armstrong-Tran-Yu from 8 years ago. So what they do is they actually construct the effective Hamiltonian level set by level set, right? In the spirit of Lebesgue integration, not Riemann, okay, like this. So you fix a lambda. Remember what we're saying, good theta means for every theta there's a lambda. Now we're going to fix a lambda and ask what thetas correspond to that lambda. We're going to do it the other way around, okay? So let's go to the class of separated Hamiltonians, this rich class. I'm going to, just for convenience, assume that V is between 0 and 1 like this, and I'm going to throw in some amplitude parameter beta. Okay, that's to remind you. Now, so the auxiliary equation, right, A is 0, A is gone. So we don't have an ODE anymore, so it's like this. It's separated. And then I can just throw it to the other side. So this is what I have. So V is given to me. It's a stationary ergodic process. And I'm supposed to basically find F, right? And then the ergodic average of F, well, the expectation of F is the theta. But OK, what is G? Now, let's start with a very modest G. I call this, so this is called a quasi-convex G, meaning that it's a single well. Decrease and then increase, OK? So quasi-convex is used in other manners in analysis as well. So for me, it's just, this is what I mean right now, OK? Single well. So convex is a special case of this, but this is more general, single well. So in this case, you see, you give me the right-hand side. I just have to solve for F. Now, G is not invertible, but this part of G is invertible. So I can use that. So you see the right-hand side fluctuates kind of here, stationary ergodic. So you just invert it. So it will be kind of a fluctuation. Sorry, here. I messed up. Like, right? So you just have to go from the range to the domain. So I can use the left part, or I can use the right part. So for each lambda, but you see, in order for this to work, lambda, because I know v is between 0 and 1, this right-hand side is between lambda and lambda minus beta. And this better be still clearing this bar. So lambda has to be greater than or equal to beta. And for each lambda greater than or equal to beta, I get an f from this side, and this expectation gives me a theta, theta 1. And similarly, I get another f from this side by inverting this branch, using this branch. I get another theta, theta 2. Okay? And these thetas are exactly according to, right, my definition of what the good thetas. So at these thetas, the effective Hamiltonian is equal to lambda. And as you see, if I increase lambda, right, this picture shifts to the left, so the expectation shifts to the left. That means this function is decreasing in lambda, and the other one is increasing. So when you put these together, you actually get the effective Hamiltonian. You get this part. You get this part. You don't quite get the flat piece with this explanation. Where does the flat piece come from? The flat piece comes from, if you bring this down all the way, and you look at the f that you get from the left, you look at the f that you get from the right, you need to concatenate them in a certain way, and then use the comparison argument, do some bridging. I'm not going to get into it much in this talk, but it's not really difficult once you have this picture. So you see, I had this original Hamiltonian, the G part of it, that was quasi-convex, a single well. Now this is also a single well. Okay? So quasi-convex went to quasi-convex. Quasi-convexity is preserved in this picture. Now, you could consider something like this, where it's not quite quasi-convex, but it has the bumps are small, smaller than the amplitude beta. And in that case, what happens is similar, but now as you have the fluctuation in the range, you need to invert, you need to have some jumps. But you remember, what is this thing? This is little f. Little f is the derivative of capital F, which is supposed to be a viscosity solution. So little f can have jumps, it's fine. But the jumps should be in such direction so that the viscosity solution property should not be violated. So you need to be careful when you're devising this thing. So that requires some work. But then you end up getting a picture like this, where this had small bumps. Now this effective Hamiltonian is quasi-convex, meaning the bumps have been ironed out, but you might actually have some flat pieces coming from here, which I'm not going to get into. And what if you have larger bumps? So imagine a picture like this, where you have larger bumps. Then what you do is you decompose. You basically identify a point like this, and when you say, OK, I'm just going to define a G1 that is like this, but then continue like that, and a G2 that from like this. So I write G as the minimum of G1 and G2. So if I can handle G1 and G2 and prove homogenization with an effective Hamiltonian H1 and H2, then the effective Hamiltonian for G is going to be something that comes from gluing and bridging these things. Again, I'm not getting into the details, but it's a decomposition argument. It's a strong induction argument where the quasi-convex and this number 2 are the base cases of this thing. Okay? So this is kind of my way of explaining it. Armstrong-Tran-Yu actually do it in a more abstract way. This version was actually, it can be found in the PhD thesis of my student, Apo Demirelli, who's the most recent academic grandson of Raghu. And Apo also implemented this numerically. So you provide the G, you provide a stationary ergodic V, you press a button, you wait for a minute maybe, it's Python, and then it gives you the effective Hamiltonian. So it's really constructive in the true sense of the word. Okay, so now what happens is when you have an A, right? So if you have an A, so now we are back to second order. Okay, sorry, first order, second order, right? Because this is a derivative, right? So we're in the viscous homogenization, so the viscous Hamilton-Jacobi equation. Now in the auxiliary equation, we have an ODE. It's like this. So you see, before, right, we were just doing some inversion. But now we have this. So, if you go to this picture, we were like, if you're here in the range, you know that you're here in the domain. Like there was like zip. It was immediately here. Now it's going to be a delay in tracking, right? If I hold the caret here, right, this like, like it takes a while for it to, there's a delay in tracking, right? But, if I have the property that the potential is such that it stays at this level for a long time, all right, it waits for this to kind of catch up, okay, then it might have a similar kind of story. And similarly, if it's, for example, here for a long time, then in the domain there will be enough time for f to kind of converge towards that. So are we giving it sufficient time to track? Okay, are we waiting for it? So that's going to be now an assumption that I will make. I will assume that the potential V is close to 0 or 1 on arbitrary long intervals. So, so this is the graph of the potential. So here's a, so for any height you want, and any length you want, I want to say that the potential is below this height on an interval of length at least L of your choosing. I can find such an interval with probability 1. But the length is measured in this scale with 1 over A because I have it here. Okay? So whatever lower height you give me, like in that, where it's super low, whatever length you give me, somewhere I can find an interval like that. Okay? So this is a property that right now we're imposing, a condition. So this is called a valley. The other one would be called a hill. So I want to have arbitrary long valleys, arbitrary long hills in my environment. Okay? And then homogenization holds. And the proof follows the same inductive structure with the base cases 1 and 2 I showed you with the quasi-convex and small bumps and decomposition. But the details are different. It's more technical, but the broad structure is the same decomposition argument. So, and the effective Hamiltonian is qualitatively the same as in the inviscid case. This is joint work with Andrea Davini and Elena Kosygina. Now, this condition, this hill-valley condition, first appeared in the context of controlled random walks and random potentials. This was joint work with Ofer, which actually corresponds to a homogenization of a Hamilton-Jacobi equation, discrete setting, where the Hamiltonian is non-convex, but of a very specific double well structure, symmetric. And then Elena joined us, and we generalized this. We adapted this to the continuum setting. And then later, there's been some other papers with me and Davini Kosygina. And then finally, this is the end product. This is the final result in this line of work under the assumption of this hill valley. Okay, so we still so far have hill valley here. Okay, and this hill valley condition, you see, if you construct V using some kind of Brownian motion, doubly reflected, mollified, or something like that, it's going to hold, right? Because I just want this somewhere. So it has a positive probability of happening, so baryogodicity is going to happen somewhere. Right? So it's actually, from a probability point of view, it's not a very restrictive property. But of course, it fails in the periodic setting because you cannot have arbitrary long valleys in the periodic setting. So that's why it's not super satisfying. We know homogenization holds for periodic. We know it holds under hill valley, but we want to have one proof of homogenization that unifies, right? So okay, let's drop the hill and valley condition. Now, when we drop it, you see, something interesting happens. Before in the picture, for example, in the quasi-convex case, I had lambda here, and lambda minus beta was still non-negative because I had to do some kind of tracking or slowly tracking. But right now, I have no claim that there should be some kind of tracking because, the potential kind of going to go up, down, not stay for too long. So I can totally have a picture like this. And in this case, actually, F, for example, I could start on the left, and then veer into the right, and then come back. Can do like a peekaboo. It's totally fine. So the two sides of the picture actually can interact. And this does not happen in the inviscid case or under the hill valley condition. It only could happen a priori, right, from this observation, when you actually drop the hill valley condition. And so the two sides can or could interact. So with that, we had this hunch, right? And then we actually were able to carry this out, and then we have this result with Elena that we showed that in the periodic setting, actually this causes indeed a qualitative difference, and we have this striking result that when A is 1, just as an example, okay, and A is 1, so you could have a G that is quasi-convex, is periodic homogenization, so we know homogenization, but the effective Hamiltonian is not quasi-convex, right? And this does not happen in the inviscid case, or it does not happen under Hill-Valley condition, okay? So that's the difference. This was the first time that there was a qualitative difference between inviscid and viscous, as far as we know. Okay, so, and just to recap, right? So for A greater than or equal to 0, inviscid and viscous, right? If G is convex, H bar is convex. So convexity is preserved. Quasi-convexity is preserved in the viscous, in the inviscid case, also under Hill-Valley. But now we just told you that when A is 1, for example, it's not necessarily actually preserved. So this also means that our hope of proving homogenization in the Armstrong-Tran-Yu spirit with the decomposition, the strong induction, is not going to work, right? So it took us a long time to realize that, because we were trying to use it, and then it took us a long time to realize that, oh, it's impossible, it's futile. So then we kind of went back to the drawing board, and then we were able to prove homogenization in the stationary ergodic setting for A positive without imposing any Hill-Valley condition whatsoever, so it includes periodic condition as well. We proved homogenization. Okay, so what did we do? How did we do it? So the approach is very soft. So recall the auxiliary equation, right? So we had this auxiliary equation. And recall that E is the set of good thetas, right? And what did we do when I presented the decomposition approach, the strong induction approach? We actually decompose, and then finally we have case 1, case 2, the base cases. In those cases, I actually tell you what E is. So if you put these together, we actually, in that approach, we actually find the set E. Now, we're not going to find the set E. Instead, we will just show that E is non-empty, unbounded from below and from above, and is a closed subset of R. That's it. We're not going to know or say anything else about E. Okay? But it's important that E is the set of all good theta, right? So every good theta is in E. Okay? So that's important. So first, if E is R, I'm done. Because if all the thetas are good, then we have homogenization as I outlined before. Otherwise, E's complement, because E's closed, E's complement is open, so it's the union of disjoint open sets. Then, there's a very soft argument that shows that the lambda, right, because good theta means, for that theta there's a lambda, right, which gives you the effective Hamiltonian. Then, if you have an interval that is not included in E, at the endpoints, you have to have the same lambda. So let me just hand wave, literally, okay? Like just to show you that these are things very soft. You say that, suppose they're not the same height. Suppose it's like this. Then there's an F for this. There's an F for that. Use those two Fs to argue that you could find another F between them because you're in 1D by some kind of squeezing, sandwiching, and the fact that solutions cannot cross, that kind of stuff, to find an F in between whose expectation would be between the expectations of these, so it would be a theta between the theta of this and the theta of that, that will give me a new good theta. But hey, E was supposed to be the maximal set of all good theta. That's a contradiction. So that's how you know it's not possible. So this is the spirit of the soft arguments I'm talking about. Okay? So, and then you basically say, okay, for all the good thetas, the effective Hamiltonian is going to be just lambda. And otherwise, you just do interpolation with horizontal lines. And then you, but again, remember, right, in Lyons, Papanikolaou, Varadhan, they said derivative theta, there's a lambda, and that lambda is not explicit, right? It comes from compactness. Again, this is not explicit in our case. Why? Because it comes from a definition of being a good theta. So again, that's like the downside of the soft approach. It doesn't tell us what the effective Hamiltonian is. Okay, so we get this kind of picture. And you see, I drew this on purpose like this, so it could be, not monotone, for example, in some stretch like that. So it could have weird shapes like this. We just don't know. And so really, the proofs use nothing technical. The short paper, and it's really using obviously solutions of ODEs don't cross, right, by uniqueness, and it uses really stuff like, even if I have changed the lambda, then two stationary solutions of this ODE, even with distinct lambda, cannot cross if they're stationary, because they have to kind of come back and do the same thing. So this kind of very, very naive-looking, mild observations actually are at the core of the proof. So I just want to summarize. So as epsilon goes to 0, for p almost every omega, this Hamilton-Jacobi equation homogenizes to this inviscid one, like this, in the general stationary ergodic setting, i.e. without any periodicity or Hill Valley condition imposed. And the proof is rather soft and simple, but H bar is not explicit. However, when A is 0 or under the Hill Valley condition, then there is a more complicated decomposition argument that gives the effective Hamiltonian. So thank you for your attention. And thank you, Raghu, for everything. And I hope that you have many wonderful trips around the world in the next few years.